This presentation is about gully erosion. Gully erosion is a very important land degradation and contributing with sediment to the sediment yield of rivers. But in this presentation, we will analyze also other waterways that are contributing to the sediment yield of rivers. The study is conducted in Ethiopia, northern Ethiopia, in the Blue Nile basin. In Ethiopia, however, gullies are found everywhere. They are found in humid highlands as well as in arid or semi-arid lowland. Nevertheless, although gullies are contributing with a lot of sediment to the river system, they are not commonly considered in soil erosion model. This map by Tababu shows us how much is the contribution of sediment yield from gullies. You can see in Ethiopia it has been calculated 94%, maybe it's a bit high, but anyway, it's an important contribution. Our study areas are, as I said, in the Blue Nile basin, in three areas, Aba Gerima, Guder, and Dibate. These areas have different characteristics that we will see in a while. We measured 94 gullies in the field, and we measure the cross-section geometry, several cross-section geometry, measuring top width, bottom width, depth, and the area of the contributing runoff area and slope. Some basic information about the study catchment and study areas. Guder has an elevation between 2,400 to 2,800 meters above sea level. Aba Gerima is intermediate, 1,900 to 2,200. And Dibate is the lowland, between 1,500 to 1,700. Rainfall, of course, is highest in Guder with 1,900 to 3,400 millimeters per year. Aba Gerima is intermediate, 800, 900 up to 2,000, and Dibate is 800, 850 up to 1,200 millimeters per year. Average size of gullies are reported herein as well, and you see that average top weight is about 6-7 meters in Guder, and 4 meters in Aba Gerima, 5 meters, 0.8 in Dibate, and so on. Depth is ranging is around 250. And gully length ranges from a few meters to about 100 meters. So we have a very large variety of size of gullies in this study. The data show some interesting results. In this diagram here, you can see that an increase of contributing area corresponds a lower slope that is necessary to start a gully. So this diagram also is very useful because we can determine that in the study area, it is necessary a minimum upslope drainage area of 0.15, 0.2 hectares to start a gully, and that gullies normally do not form for slopes less than 0.6, 0.65, 0.9, 0.09. So most of the gullies are in the range of gradient that is less than 10 degrees. The data was used also to correlate the gully area to the volume And we got very nice result with a correlation coefficient of 0.95 on using 94 gullies. And that is very important because from measurement of Gully area, from aerial photographs, for instance, or satellite image, you can calculate also the volume. So you can calculate also how much material has been lost in a gully through time with monitoring in the different intervals of time. This correlation has a high coefficient, correlation coefficient, and this is why probably, because as we observe in another gully in the Rift Valley in Ethiopia, by field measurements of the gully size across 9 years interval, you see that top width has been increasing almost constantly, whereas depth remains more or less the same. So with an increase in top width, we have an increase also of the volume that is lost. This is the list of images that we have used to investigate on the formation of gullies in the study area, starting from 1957. These maps show the density of gullies. The different colors correspond to different timing of the survey. And you can see that in the three study areas, there are different densities. For instance, in Abagarima, this figure B, we have a lot of gullies scattered across the whole catchment. In Dibate, these catchments here, they are very few and concentrated mainly in the lower part of the catchment. And in Gudar, we have the most of the gullies concentrated across the divide between the two catchments and also with other catchments. So from this data, it was possible to build this diagram here, where we have the increase of gully density through time. And the increasing gully density through time in the different areas is expressed very well by an exponential function of this kind. And the correlation coefficient is rather high, with the exception of Sahai catchment. All the other catchments, the R square is 0.98, 0.99. This diagram here has another interesting correlation between gully length and volume. And also it is a good correlation with relatively high correlation coefficient. And these coefficients can be used, these equations can be used to calculate the volume of gullies, simply measuring the length of the gully itself. In the Rift Valley gully, we observe an increase of the size of the gully through 9 years' time, and the interpolating function is again exponential, although with a little bit different coefficients. But the correlation coefficient is 0.9, so it's quite high as well. We have an increase through time of the gully density. But what about rainfall? Unfortunately, we do not have hourly intensity in the study area. And in order to try to point out the role of rainfall in terms of intensity and duration, we develop a very simple parameter, just counting the days with rainfall higher than 20 millimeters in 24 hours, just to give a rough idea of the rainfall effects. And you can see here that although the gully density is increasing, there is not such an increase in rainfall intensity, with the exception probably of Gudar, when there is a little trend. But the other two sites do not show an evidence of an increasing trend of the number of days with high precipitation. So it seems from this result that rainfall, okay, is important, but probably not in the way that has been considered in past studies. And in order to explore further these hypotheses, we decided to investigate if there is any effect of subsurface water level fluctuation on gully head retreat. And we placed some piezometers around the gully head, and we measure also sediment yield, sediment transported at the outlet of the gully, of the gullies, actually. This diagram shows that the response in the change of subsurface water level is very fast. So there is a very fast response, and fluctuations follow clearly the fluctuation in the rainfall intensity in one day. And you can see from here, you know, there is the decaying fluctuation level water in the soil. So these data led us to produce this diagram. In this diagram, we can see that with the level of the subsurface water approaching the surface, that is approaching saturation condition throughout the whole profile of the soil, we have more gully head retreat. So this diagram tells us that subsurface water fluctuations and saturation conditions are very, very crucial, very effective in controlling or causing gully head retreat. In this table here, we have data about the gully head retreat, the volume of gully head retreat, and the soil loss measured at the gully outlet. And we can see that in Gudar we have 22 gullies, in Abagarima 18, in Dibate 16. So it's quite a good number of data. But the volumetric gully head retreat varies quite remarkably among the different study areas. So we have about 7 cubic meters per year in Gudar, as far as 42 in Dibate. But the most interesting thing is that the contribution from gully head retreat is the most important in the soil loss, in the sediment that exit the gully. As you can see, 7 in Gudar is about 90%, 80%, 85% in Dibate, and so on. Another interesting issue is that in Gudar, the average soil suspended sediment yield measured by a bubble is about 33 tons per hectare per year. And these data tell us that 22 gullies contribute for almost 1/4 of the total soil loss of Gudar. So this is a result proving that gullies are really important in contributing to soil loss and sediment yield. But gullies are not the only waterways. Gullies are very well known, very well studied, but there are other waterways, especially footpaths like this one, that are never considered in soil erosion models. But you can imagine how much sediment is removed through these footpaths during high intensity rainfall, especially during the monsoon time. In Ethiopia, in this area, we have one main rainy season, and 80% of the rain fall during this short rainy season. So you can imagine how much sediment. So the contribution of these waterways, of these footpaths, is completely neglected by soil erosion models. But they are important, as you can see here in this Google Earth image. You see that this footpath is quite eroded. And again, waterways showing a washout splay, reaccumulation of sediment here, and here as well. You know, there's quite a large accumulation, a splay of sediment coming from the gravel road running nearby. Not only footpaths, but also degraded areas. There are scattered degraded areas in the study areas. They are generated by different processes. Gully expansion or landsliding. But from this preliminary investigation, it seems that landsliding is the main process that starts degradation in so large areas, because the first slide may create some instability condition. They are mainly shallow landslide. And then the instability conditions propagate through the areas, fanning out into quite large areas degraded with bare soil. See other flow or reactivation landslide are example what was already saying. Using Google Earth image, we map the waterways in green. We consider only those anthropogenic waterways connected to the river system that have a real connection to the river system, that is really contribute to the sediment yield. Then we have degraded areas in yellow and landslide in blue. I will repeat the same in the three areas. Here you can see that in the Quechua catchment, which is a so-called treated catchment, that means is highly cultivated with soil and water conservation practice, compared to Laguna that is not treated and where soil and conservation practices are very, very few or almost non-existent. And again, the same situation here in the Bate area. The result of this analysis tell us that the density of waterways is much higher in the treated catchment of Abagerima compared to the untreated catchment of Laguna. And in Dibate, we have more or less the same density. Sorry, in Guder, more or less the same density. In Dibate, the situation is similar to Abagerima, with soil and water conservation practice catchment with a higher density of waterways. So we should expect to have an important contribution of sediment coming from this catchment. A similar situation is observed if we consider the percentage of the land degraded. Again, in Abagerima, the treated catchment has a higher percentage of degraded land. In Guder is a little bit less in the treated catchment, and in Dibate the same. So we should expect to have not so many degraded land in treated areas, but probably they started before, and probably they started to implement soil and water conservation measures just to decrease the soil erosion in this area. Another interesting issue is that in the soil and water conservation catchments, runoff is reduced by 44 to 65% according to Sultan and others. But this data is coming, this result is coming from measurement as at plot level. But what is going to happen in a catchment where you have so many waterways? They contribute a lot also, not only for the sediment supply, but also to convey overland flow. So this aspect should be investigated in more detail. Secondly, we have in Gully, according to Ababu data, that sediment yield is much larger in the untreated catchment rather than in the catchment in Gully, where we have the soil and water conservation measures. In the case of Gully, drainage density is more or less the same, but the situation is very different if we consider degraded land, and especially if we consider, as we have seen in the previous slide, that in acoustic there are many landslides, so they can contribute to rise the quantity of sediment delivered to the rivers. So to conclude, we can say that Gully triggering growth is substantially affected by upslope drainage area, slope gradient, groundwater level fluctuations. So these are very important factors, probably the most important factors, including also soil characteristics that were not considered here. Gullies form mainly on gentler slope, less than 10 degrees. And the contribution to sediment yield of gullies, waterways, and degraded areas and landslides was not quantified in these studies, which is quite preliminary. However, we demonstrate that they exist and they can act at a very high rate in transferring sediment and water to the river system. So they should be included in soil erosion model and also in hydrological models. Therefore, since they are not considered up to date in these erosion models, therefore we need to improve the knowledge on these waterways, sources of water, and sediment and transfer of sediment. So we need more investigation on this topic. Thank you very much.